This talk is about stochastic processes, of which we introduce temporal statistics, ergodicity, and memory. Temporal statistics are a sort of different statistics respect to the statistic of ensemble. Here we have 5 realizations of stationary processes. If we take a single column and we average over infinite realization, we have the mean value. Then we can define another mean, that is a temporal mean, that is the average along the column. This is either the integral or the sum of all the number divided by how many we sum, and this is a temporal mean. Well, the temporal mean is sort of related to the stochastic mean. In fact, if the process is stationary, we can show that the temporal mean, that is stochastic, changes from realization to realization, but in the average is a true mean. The question is the temporal mean really the mean? Well, this depends on the variance, and we will show it later. As we define the temporal mean, we can also define the temporal correlation, covariance and autocorrelation, and so on. These are just the definition of the autocorrelation or the autocovariance, that is a product of two samples at a distance tau, again measured only on one realization. And here I make an example in which I take two processes. The one on the left is a continuous time process. The one on the right is a discrete time process. But beside the continuous and discrete time, they have different behavior that are captured by the autocorrelation. The autocorrelation is in the row below, and you see that for the continuous process, the autocorrelation, it is always maximum in the origin, but then degrades slowly, and after 20 seconds it goes to 0. After is more or less very small or 0. We can say that this process decorrelates in 20 seconds. And if we look at the shape of the signal, we see that the signal keeps a sort of continuity. That is the sort of memory we have to face with. On the discrete process, if we compute the autocorrelation of this realization, we see that the autocorrelation is 1 in the origin, as it should be, and it's 0 for any other sample. So it means that closely related samples of this process are totally uncorrelated, means that they are not linearly related. And this process is very, very rough. And we can say that it has no memory. So in general, we can always derive a discrete process from a continuous one, the blue, by sampling, and the discrete is a corresponding red process. If we compute the mean, we find that the mean of the discrete process is the same mean of the continuous process. And if we compute the autocorrelation, we find that by definition of the autocorrelation of the discrete process, we have the autocorrelation of the continuous time process sampled at the sampling rate that we fix to derive the discrete process. For example, if we take the blue process, the same before, that decorrelates in 20 seconds, and we sample it exactly at 20 seconds, we will have the red process that is uncorrelated. And you see, in fact, that is no continuity, but it's very rough process. Well, let's put together the temporal statistic and the ensemble statistics, and we got the ergodic processes. What are the ergodic processes? In simple terms, is processes where the temporal statistics and the ensemble statistics are identical. You can speak of mean ergodic, you can speak of wide sense ergodic, depending if this holds only for the mean or also for the covariance, but in general, the idea is provided in this plot. Usually we need a lot of realization, infinite realization. Now realization are a column. But the process is stationary, so if just we take one sample from the different realization, we get an idea of the statistics, that is the blue signal. However, the blue signal resembles very much the behavior of any other column. And in this case, we can say that the process is ergodic. Let's make an example of a process that is made of cosinusoid. We already discussed of it in the previous talk. These are all cosinuses, but what changes is initial time, so shifted cosinusoid. And here in red, you see, for example, how we compute the statistics autocorrelation at time t. You see, if we pick a time t, that is the inverse of the frequency, we have always the same sample, and so the product is always a squared value. And this clears that the autocorrelation is 1 at t. But we can also compute the temporal correlation by averaging the product of two samples at distance t, so the one in the blue line. We need another couple of samples, another couple of samples, and so on and so forth. In this case, we can tell that if we do average in time domain or in the ensemble domain, we get the same result, that is a cosinusoid. And this process is stationary and ergodic in second-order statistics. Then this is an overview for the general cases also of two processes. So as we can define a temporal mean, and we can define the statistical mean, so in blue are the statistics and in red are the temporal statistics, we can generalize to the correlation, cross-correlation between two processes, that is a product of two samples at a certain distance. We can generalize to the cross-covariance and to the normalized cross-covariance, that is also the Pearson correlation. So this is all, and let us now make an example of how can we estimate the mean and the autocorrelation. Yes, because the ergodicity tells a very important thing, that if the process is ergodic, we don't need all the realization. It's enough to have one. However, one realization is infinite. Usually we have only one piece of realization. Then if we compute the statistics only of that piece, we have an estimate of the mean or an estimate of the correlation. Are the statistics good? Well, if they are good or not, we can evaluate, for example, in this case. In this case, we deal with the estimate of the mean. Then, when we want to estimate of the mean, for example, of discrete sample, we sum all these samples and we divide by the number of samples we sum. Is this estimate good? Well, in the mean, by using the property of the process, we can say that the mean value of the estimator is the true value that we want to estimate. That is a good. But it's not enough. It's not enough to have convergence in the mean. We also need that the variance is zero. And here again, by the virtue that all the samples are independent, if they have a variance of the sum for independent samples is the sum of the variance, and we see that the variance of the estimate decreases inversely with n. So this means that as n goes to infinite, also the variance is zero, and then the mean is a good representation. But what happens is so good? Let's make an example. We want to know if the coin is biased or not. If the coin is fair, it should not be biased. How we can get it? Let us assign two values, 1 if id and -1 if tail, then the mean value should be 0. But of course we need to estimate the mean value, and the estimate improves depending on the number of tosses. So this is here a simulation in which I show you the result of the estimate as the number of tosses increases. And you see that as the number of tosses increases, the mean value is 0 plus minus something that is reduced as far as the number of tosses goes to infinite. Well, I use the standard deviation as an idea of the boundary, and you see that the standard deviation is 1 divided by square root of n. So this means that if we do only one tosses, we cannot tell that it's biased because we can have either 1 or -1 with the same probability, but if we have 100 of tosses, the standard deviation is 1/10. So the accuracy in which we can say the coin is biased or not is 1/10. Of course, if we want a better accuracy, the number of tosses should be very huge. So, for example, if the accuracy we need is 1/1000, so we need 1,000,000 of tosses, and this is a huge number. So we really need to observe a lot of events in order to have a very good estimate. And by the way, if we are the one that know that the dice is biased, and we always bet in the good direction, and we bet €1 per time, in 1,000,000 of tosses, in the average we get a significant gain.